Hello everyone, welcome back to our series on energy modeling applications with Honeybee. And in the previous video, we dove into understanding why conditions were thermally uncomfortable in our single family home energy model here. And we realized that they were primarily the result of these surface temperatures that you see previewing in the scene here. And we found that even though the heating and cooling systems were meeting the thermostat set point and the air temperature in these rooms was at that desired temperature, the fact that these surfaces were so different from each other from that air temperature was ultimately contributing greatly to the discomfort in these spaces. So in this video, we're going to take a bit of a break from this single family home, and I want to show you guys one more graphic that you can use, particularly to help communicate this type of discomfort to a client or a team member. Because certainly we've gotten a lot of understanding ourselves by looking at detailed graphics like these surface temperatures, but these may not be as immediately accessible to other team members or other people. So in this video, we're going to be covering a famous graphic that many of you may know already called the psychrometric chart. Okay. So for those of you who haven't seen a psychrometric chart before, I'm going to give you like the 30-second breakdown of this. The psychrometric chart is basically a plot of temperature on the x-axis here, and you'll have a plot of humidity here on the y-axis. And so you have lines of constant temperature like what I've just described here. And these are typically meant to be the temperature of the air, though they can also be the operative temperature, as you'll see we're going to use in a little bit. And very importantly, though, these lines of humidity on the y-axis, they are not what we are typically seeing in weather reports as humidity, which typically they'll give you a relative humidity as a percent. This, however, is absolute humidity. It's not relative. Another word for it is the humidity ratio, or the total amount of water vapor divided by the total amount of air. So it's literally actually the mass of water divided by the mass of air. And you can see under reasonable situations that never really gets to be more than 3%. I don't think on Earth you'll ever find many conditions where naturally you'll find more than 3% of the actual air around you is water vapor. Typically it's much more around 1%, but that 1% can still make a very big difference. So next we have what we call the saturation line. So at a certain point when the humidity ratio gets so high, you cannot literally fit any more water vapor in the air, that it has to start condensing out essentially. You've reached the level of saturation, the maximum amount of water that can be in the air. And you can see that the warmer the air gets, the bigger the space you have in between those air molecules, and therefore the more water vapor you can actually fit in the air. So that's why we have this kind of swoopy graphic here. And that's also why each of these lines of relative humidity, or the percentage of the actual level of saturation, that's why these are also very swoopy. Because essentially as air gets warmer, you can fit more water vapor into it. So, all right, so this is all very basic fundamental physics. What does this actually have to do with thermal comfort? Well, a very common practice is to actually plot a comfort polygon on the psychrometric chart, just like you see here. And this particular type of comfort polygon that you're seeing right now, this is derived from the PMV model. So there are actually assumptions about clothing and metabolic rate, and even the airspeed that is getting you to draw this type of polygon on the chart. And so if we have the chart set up like this, what we can easily do is, many of you may already be familiar with this practice of plotting outdoor temperature onto a psychrometric chart like this. And so a lot of people will do this in an early stage of design to get a sense of what types of passive strategies maybe they might use to get certain hours inside the comfort polygon. So for example, in this case, we have a lot of these hours that are colder than comfort. So maybe I can use some internal heat from lights and equipment. If I capture that well, I could get more of these hours inside the comfort polygon. And yeah, and certainly it's helpful to see what percentage of hours are already inside the comfort polygon to begin with. So this is a useful exercise for outdoor temperature, but just as you guys have seen in the previous video, we can also do the same thing with the indoor temperature and the indoor humidity that we can get from our simulation. And so that might look something like this, where we're seeing the vast majority of hours are pretty closely inside of that comfort polygon. In this case, maybe you have a few of them outside of it, but more or less, right, a lot of the hours, if things are designed well, if the system's working as it's intended to, then most of the hours should be inside of there. But you can see this is specifically for a design that has a 30% window to wall ratio. And I should say I'm actually plotting the zone operative temperature here. So I'm trying to account for both the temperature of the air and of the surfaces when I make a plot like this. And so let's say if I were to change this window to wall ratio to be something very different, maybe a lot higher, around, let's say, 90%. And you can see because of that higher window to wall ratio, the higher amount of sun coming into the space, and probably also because of the higher amount of conduction and heat loss that we get when the sun isn't shining on it, we suddenly get all of these hours pretty far outside of the comfort polygon. And some of these are getting way up there, up by, let's say, wow, like 86 Fahrenheit in some cases, or that would be something like 28 Celsius. And we can see that only 51% of the time is now inside the comfort polygon. And there's actually a lot of real world evidence to show that this probably describes a fair number of the buildings that exist out in the real world. For example, let me show you some data from one of my favorite studies that was conducted at the Lawrence Berkeley National Lab by these two awesome scientists over here. And what they did was they surveyed over 50,000 occupants across 350 different buildings, and they surveyed the occupants about their satisfaction level regarding various different criteria in their buildings. So they looked at ease of interaction, amount of light, amount of space, visual comfort, colors and textures, all these different things, air quality, and they also asked them about the temperature in their space. And they took the results across all these 50,000 occupants, and they tried to do these little box plots that you see here. So the lower boundary will show you the 25th percentile, the upper boundary will show you the 75th, and then you have the mean and the medium in the range here. So according to this, people are mildly satisfied with the design of their workspace in this case. And maybe there are 25% of people that we can say are not satisfied, that have a negative rating for their satisfaction with the workspace. So they do this for all sorts of different criteria, and they kind of ranked them even in terms of how satisfied versus unsatisfied people were with them. And one thing that you guys will notice across all these different criteria is at the very, very bottom, we have temperature. And like amazingly, like the results that you find with this are kind of stupefying almost, that we find that less than half of occupants are satisfied with the temperature in their buildings. And more than 25% of them are actually very dissatisfied. They report themselves being very dissatisfied with the temperature of their buildings. And I mean, granted, we do have maybe something like 25% of the people that are at least better than a satisfaction level of 1. But I mean, still, I mean, more than 50% of occupants being thermally dissatisfied. This is far from what our lofty goals are with PMB and getting below 10%. Clearly, we're not meeting the goals, and clearly there's a lot that the industry has to do to improve thermal comfort in our buildings. So, all right, now that I hammered home this concept to you a lot, that thermal comfort really is a big issue, and it is something that you really can use to argue for certain strategies, let's go back and do an exercise. So I'm not going to go back to the single family home, but I want you guys to go over to the samples that we've been working from. And again, I'll put the link to this specific sample file in the description of this video. But if you guys can open up this shoebox thermal comfort model, this will give you a small, simple example that you can use to understand the relationship between the design of at least of a shoebox and then the thermal comfort as it stands on a psychrometric chart. So give it a few seconds. This file is just opening up here. And I'm going to go over to top view so we'll be able to see what's going on here. Well, maybe I'll first show you in perspective view, right? We just have a little shoebox here. We have one side that's exposed to the outdoors with a little window. And this is a parametric model, so you can actually change the ratio here of the windows as well as the orientation of the box itself. You can rotate that around. So I'll just leave this at 30% and 180, perfect south-facing shoebox. And you'll see that, yeah, there's not really too much else to this model. You'll see that I'm taking out the occupancy schedule here, basically that object that is dictating when the space is occupied. And we're going to use that to essentially look at just the occupied hours on a psychrometric chart here. But let me just go ahead and run the simulation here. So I'm going to double click this little toggle that is set to run the simulation component here. And you'll see it's going to simulate the shoebox model, and we're going to get operative temperatures out of this as well as relative humidity, which we can then plot onto the psychrometric chart. So, all right, I'm going to go over to top view so we can see this. And so you can see a few different graphics here, which we can relate back to the grasshopper scene. So one thing is that we have this hourly plot here, and this is showing us the operative temperatures in the space over the course of the day. Granted, it looks like they aren't going too crazy in this case. Maybe, yeah, they're going down to maybe 19, a little below 19, and going up to 26 Celsius. And perhaps more importantly, we can see the relationship between these temperatures and the actual thermal comfort polygon here, this PMV comfort polygon, which you can see has its own dedicated component. So this is actually what's plotting the polygon on the chart. We have a separate one that's actually drawing this whole visualization of the psychrometric chart for us. And you can see that I've plugged in the data of occupancy here, basically our occupancy schedule values that are just fractional values like you see here. And I want to make sure that I'm only looking at the occupied hours. So I'm using a conditional statement here, which you guys are probably already familiar with from our previous videos, but I'm using that to say, okay, only plot the occupied hours on this chart here. So, all right, so we can see that our comfort is pretty good in this case, right? We have actually, in total, we have 98% of these occupied hours are comfortable inside this comfort polygon. But remember, right, this is a south-facing room, and the glazing ratio right now is at 30%, which generally speaking is pretty low, or our code typically tells us as a baseline to not go much above 40%. But let's say this is, a new type of office that is all glass, which I know is very, very popular these days. So let's see what actually happens when we go and make this shoebox 90% glazed, we'll say. Maybe we won't go all the way to 100, but we'll say 90%. And if I let the simulation run with this, which will take just a few seconds, we'll see how much our temperature plot changes. And yeah, look at that. Whereas before we had 98% of the hours were inside that comfort polygon, now we're getting a significant number of hours falling outside, particularly a lot of hours that are much warmer than what we'd hope to be inside the comfort polygon here. And I can even go over to the polygon here, and I can see, yeah, it was 98% before, and now it's dropped all the way down to like 70 practically. So we can literally see, right, the heating and cooling system are still working the way that they're intended to in this model. This is just because of those operative temperatures that we're getting conditions that are far outside the comfort polygon here. And the nice thing about a graphic like the psychrometric chart here is that it not only shows you the percentage of time that is inside the comfort polygon, but it also gives you a sense of how far outside of the comfort range you're getting in some of these hours. Because we're getting up to, let's say, like 28 Celsius here, which is pretty far outside the comfort range. And we're going all the way down to 18 Celsius in some of these other conditions. So, all right, so I'd encourage you guys to take some time after this video and play with some of these inputs of the ratio and the orientation here. Let's say if I were to make this room facing west, you guys will see that that's going to have a whole different set of discomfort conditions as a result of doing an all glass facade on that. But generally you'll find if you make the windows smaller or if you shade the windows, that's going to generally make the space more comfortable. So it gives you a good way of arguing for these types of strategies like lower glazing ratios, better performing glass, better shading. A lot of these things that are often difficult to justify with energy savings alone, you can usually make a case for them with thermal comfort. So, all right, so we've done enough on the fundamentals of thermal comfort. If you guys can't tell, this is one of like subjects that are near and dear to my heart. I can do a whole series just on thermal comfort itself, and maybe one day I will do one of those. But we got to get back to the energy modeling applications that this series is about. So in the next video, we're actually going to start to set up a strategy and understand the constructions of the single family home model that we've been working on, so we can then propose some better constructions and evaluate thermal comfort in terms of those. So thank you guys for sticking it through this video. I hope it was helpful, and I'll look forward to seeing you in the next one.